Today we will learn phasor and phasor diagram. Phasor is a rotatory vector which is used in the analysis of AC circuits, resistive circuit, inductive circuit or capacitive circuit, or in LCR circuit too. So phasor is a rotatory vector and it gives phase relationship between instantaneous current and instantaneous voltage of any AC circuit. It also helps in the analysis of any AC circuit. So let me take firstly a purely resistive circuit and its instantaneous values of current and voltage. V is equal to Vm sine omega t. This is instantaneous voltage of purely resistive circuit. And I is equal to Im sine omega t. So now let us draw the phasor diagram. Here I have taken x-axis and from origin at an angle equal to phase angle omega t, here taking one angle omega t, let me draw a vector. This is a vector which is at angle omega t and its magnitude will be given by voltage amplitude in case of voltage phasor. So we have two kind of phasors. One is voltage phasor, another one I will draw for current phasor. So the magnitude of this rotatory vector, which is rotating in anti-clockwise direction and has magnitude equal to voltage magnitude. And when you take its perpendicular component on y-axis, this is your y-axis, and the perpendicular component on y-axis of this voltage amplitude gives you instantaneous voltage. Here it is your instantaneous voltage. So voltage phasor is a rotatory vector is rotating in anti-clockwise direction. And at a certain time it is making angle equal to the phase angle of instantaneous voltage, that is omega t. At any time t, it is making phase angle or angle with x-axis equal to omega t. The magnitude of this voltage phasor is given by voltage amplitude. This Vm is given by Vm. And what is voltage amplitude? If you draw a instantaneous voltage versus angle curve, here you have angle omega t or theta whatsoever. So, and here you have instantaneous voltage. Then the highest value, this value is called voltage amplitude. So the magnitude of voltage phasor is given by voltage amplitude. And this is the magnitude of voltage phasor, and the perpendicular component of this voltage phasor gives instantaneous voltage. So now it would be clear to you, and it will help in analysis of current in any your AC circuit, in LCR circuit. So we will be doing, this was your voltage phasor. Now next one is your current phasor. In the same way, if you draw coordinate axis, here you have coordinate axis, and the instantaneous current value is given by Im sin omega t. The phase angle is omega t. So at any instant t, if a vector is there, rotatory vector is there, which has magnitude equal to current amplitude and which is at an angle equal to phase angle of instantaneous current, that is omega t, then such vector is called current phasor, and it rotates in anti-clockwise direction. The magnitude of the phasor is given by Im and its perpendicular component. Here you can take its perpendicular component. This will give you instantaneous current. Perpendicular component of the current phasor along y-axis gives instantaneous current. So these are the two phasors, and when you draw the two phasor on the same diagram, because in case of purely resistive circuit you can see the phases are same, so the two phasors, voltage phasor and current phasor, will be at same angle omega t because the phases are same. and the magnitude of this current phasor is given by Im, current amplitude, and its perpendicular component on y-axis is given by instantaneous current. So this is the case of a purely resistive circuit. Now when you take a purely inductive circuit, you have instantaneous voltage given by Vm sine omega t, and as we obtain instantaneous current lags behind in phase with the voltage. Instantaneous current has phase smaller than this phase by pi by 2. So when you draw phasor diagram for the two instantaneous voltage and current, then you will find that voltage phasor is at an angle omega t. This is your angle omega t, and its magnitude is given by voltage amplitude. Now current is having a phase pi by 2 less than the phase of voltage. So take a vector at an angle pi by 2 less. Here you have a vector which is at an angle 90 degree smaller in phase with your instantaneous voltage. So its magnitude will be given by current amplitude, and they have their perpendicular components on y-axis given by instantaneous voltage. And here when you take the perpendicular component on negative y-axis, then you will find instantaneous current. So the magnitude of this phasor gives you is given to you by current amplitude, and this is at an angle 90 degree less than the phase angle of voltage instantaneous voltage. So this was your phase relationship between instantaneous voltage and instantaneous current in a purely inductive circuit. This is the phase relationship. Now in a purely capacitive circuit, in which voltage given by instantaneous voltage is given by Vm sine omega t, and instantaneous current leads the instantaneous voltage in purely capacitive circuit by pi by 2 in its phase. So I is equal to Im sine, here phase angle is larger by pi by 2. So omega t plus pi by 2. And we are to draw phasor diagram, phasor vector in purely capacitive circuit. So let us draw the phasor diagram for voltage phasor and current phasor. So phase angle is given by omega t at any time t. So at any time t you can draw a vector which is at an angle omega t from x-axis. And what is x-axis? This is your actually omega t only. And then the magnitude of this phasor, voltage phasor, is given by voltage amplitude and its perpendicular component. Here you have perpendicular component given by instantaneous voltage V. Now current is leading the instantaneous voltage in phase. Here you can see the phases are different. Instantaneous current has a phase greater than pi by 2. So here we should make an angle equal to pi by 2, 90 degree, and we should draw a vector. This vector gives you current phasor. This is your current phasor, and this was your voltage phasor. And current phasor is given by, the magnitude of current phasor is given by current amplitude, and its perpendicular component on y-axis is given by instantaneous current only. So this was all about phasor and phasor diagram. This is your phasor diagram for a purely capacitive circuit. Now analysis of instantaneous current in an LCR circuit. Where the instantaneous voltage provided to the circuit V is given by Vm sine omega t. So you have been given instantaneous voltage and you have series LCR circuit, means you have one resistor, one inductor and a capacitor. All the three are connected in series. It is your LCR series circuit. And then it is finally connected to an alternating voltage source with value V is equal to Vm sine omega t. And the resistance given is R, inductance given is L, capacitance given is C. Now this voltage will drop at all the electrical components. The voltages will not remain same since the circuit is a series circuit, so current will be same in all the components. So let the current in all the three electrical components be I is equal to Im, and obviously you have seen that in capacitive circuit there is phase difference in instantaneous current and instantaneous voltage. Similarly in your inductive circuit. So here will be a phase difference. Phase will not be same because you have capacitor and inductor in this circuit. So you cannot write the phase of instantaneous current as omega t. So let me take the phase of instantaneous current as omega t plus phi. Means it has increased in phase by angle phi. So for finding instantaneous current in LCR circuit, we know already this omega t. We need to find current amplitude and phi only. If we find these two things, we can find instantaneous current. So we have assumed that this is your current flowing through the circuit. I is equal to Im sine omega t plus phi. Now this voltage will drop on all the three electrical components and voltage will not remain same because in series voltage varies as per the consumption. So let voltage V is divided equally on all the three components, VR plus VC plus VL. So this is the voltage which is dropped across the three components. Now these voltages are actually the perpendicular component, this component. It means instantaneous voltages. Here we have taken instantaneous voltages VR or VL or VC. These are the perpendicular components of phasor VR amplitude maximum voltage, because phasor is given by a voltage amplitude, VC M an amplitude of that, therefore I have written M. M stands for maximum value of voltage and maximum value means amplitude, and VC across R resistor. So if perpendicular components are added to main your voltage, so your voltage amplitude Vm also should be given by, this is your phasor rotatory vector voltage amplitude should be given by the sum of the three. Vm R, I have changed the position, I have written M in front. So you can take in any way, you can take the amplitude before also, VMR, VML, VMC. So your voltage amplitude of the applied voltage, here you have applied voltage, can be given by VMR plus VML plus VMC. Now we know that, let me draw the vector. Here current is same in all the components. So along through R, through L and through C, the current will be same. Now we know that in a purely resistive circuit, current and instantaneous voltages are in the phase. Now as given, phase angle of current is omega t plus phi and phase angle for voltage is only omega t. So voltage phasor this is your voltage phasor. Will be at angle omega t at time t, and current phasor will lead to this voltage phasor by phi angle. So here you have current phasor which is given by the magnitude of which is given by current amplitude. Now we know that in a purely resistive circuit, current and voltage phasors are in the same phase, in the same direction. So this will also represent the voltage phasor in purely resistive circuit. This is your voltage phasor in a purely resistive circuit. This is subscript, R is not multiplied, this is actually your subscript. So let me write a small form, okay. And we know that in a purely inductive circuit, current lags behind by pi by 2 by voltage phasor. And here the same current is flowing through all the electrical components. You can see same current. So phase of current through inductor is omega t plus phi. And we know that in inductive circuit, current lags behind by pi by 2. So let me draw an angle pi by 2, and at this angle let me take voltage phasor across an inductor. This is your voltage phasor across inductor. given by VML. And similarly, you can find voltage phasor in a capacitor. We know that in a capacitor, the current phasor leads the voltage phasor by pi by 2. Here you have capacitive circuit. Current is leading by pi by 2 from its voltage phasor. This is your current phasor. So in a capacitor. So let me write here C subscript for capacitor. So voltage phasor will lag behind from its current phasor by pi by 2. This is your pi by 2. Here you have voltage phasor given by voltage amplitude across capacitor. So now all these are vectors. These voltage phasors are vectors. And we find the resultant of two vectors if they are in opposite direction. Suppose you have a 5 Newton force in one direction and in opposite direction you have a 2 Newton force. Then the resultant will be given by 5 minus 2, that is 3 Newton, along the larger vector. So let us suppose that VMC is greater than VML. Therefore, resultant of the two vectors is given by VMC minus VML. So this vector is parallel to VMC only. If we draw this vector with length equal to magnitude of this anywhere but parallel to VMC, then that vector will represent, here we can draw a parallel vector parallel to this VMC, and the length is given by the magnitude of VMC minus VML. So we have two vectors here and one resultant vector. So now from triangle law of vector addition, your resultant vector Vm can be taken as VMR plus VMC minus VML. So for magnitude, we know for magnitude we can we can make from vector addition. Resultant of this vector can be given by root under square of one vector VMR square plus square of another vector VMC minus VML square plus 2 into first vector into second vector into cos of angle between the two, and the angle between two is 90 degree and cos 90 is 0. So the next term need not to be written here. Now VMC is equal to, you can write VMR in terms of IR because it obey Ohm's law. So VMR is equal to IMR into R whole square. Similarly, VMC, it will be equal to IMC into capacitive reactance, which is the resistance in a capacitive circuit. So XC minus, similarly, IML into XL whole square. So therefore, Vm, voltage amplitude of given instantaneous voltage, is given by, let me take the current amplitude outside. So square of current amplitude, when it comes out, it becomes simply current amplitude into, and current amplitude it's same. The same current is passing through all the components, through capacitor, through resistor and through inductor. So need not to write the subscript like capacitor or inductor. So simply we will be writing Im, and here root under r square plus xc minus xl whole square. So if you change this quantity by Z, Im Z, then it will be of Ohm's law form, and here Z is called impedance. And you can see impedance, which is the total resistance through resistor and the resistance offered through capacitor and inductor. It is a complete resistance offered by an LCR circuit. And since it is a resistance, so unit of impedance, SI unit, is ohm. So this is how you can find current amplitude. Current amplitude is equal to voltage amplitude divided by impedance. So for finding instantaneous current, it is not given. Given thing is only voltage, and we need to find instantaneous current, and I have found current amplitude, and here omega t is given in voltage amplitude itself. Now we need to find phase angle phi in between the current amplitude and voltage amplitude, this phase angle phi. So from given triangle, let me name the triangle OAB. In a given right angle triangle, OAB, you find tan phi. So tan phi is equal to perpendicular upon base, and this is your equal to tan phi is equal to VMC minus VML divided by VMR. So this is equal to phase angle, and you can change this VMC by IMXC. Here V is equal to voltage, and from Ohm's law V should be equal to IR, and through capacitor the resistance is actually capacitive reactance, that is XC. Similarly, here you can write IMXL divided by IMR. Therefore, tan phi becomes equal to, on cancelling Im from numerator and denominator, you get XC minus XL upon R. So this is the phase, and I have already obtained current amplitude. So you can find the current now, instantaneous current. Now there is one term, impedance diagram. So if you draw a triangle with R as one side, XC minus XL as another side, then this hypotenuse is given by impedance Z, because R is a vector, XC minus XL is a vector, and the resultant is your impedance. So this diagram is called impedance diagram, and here you have angle phi. So from impedance diagram, you can find cos phi is equal to base by base R by hypotenuse Z. So this was about impedance diagram. There is many disadvantages of using phasor diagram for the analysis of an LCR circuit. Firstly, it does not say about the initial phase of an LCR circuit. So it gives only a steady state solution. Now it does not say about the states of LCR circuit when voltage is equal to 0. So it does not offer a transient solution. It offers only a steady state solution. Though the solution of an LCR circuit should be sum of steady state solution and a transient solution.